Hello everyone, welcome back to Chemical Engineering Investment channel. As you know, these days we are focusing on the module of heat transfer operations. So in this regard, we are bringing the lecture number 5 for our valuable viewers. In our previous lectures, we have studied the difference between the thermodynamics and heat transfer. We studied the definition and introduction of heat transfer, the driving force, the applications of heat transfer. Then we studied the modes of heat transfer, including conduction, convection, and radiation. We studied briefly about all these three phenomena. Then we started about the conduction. We have seen how the phenomena of conduction takes place. Then we studied the Fourier's law of heat conduction, and then we had solved an example related to the Fourier's law of heat conduction. In our today's lecture, we will move to an important parameter in the Fourier's law of heat conduction, and that is the thermal conductivity. So, firstly, we will see in our today's lecture about the introduction of thermal conductivity. Then we will define it, how we can measure the thermal conductivity of a material, and then we will have some final remarks about the thermal conductivity. So, if you have not subscribed to the channel yet, please subscribe to the channel. Click on the bell icon to get all updates related to this channel. Before starting the thermal conductivity, let's recall an important concept of specific heat capacity, which is Cp, represented as Cp, which is the ability of a material to store thermal energy. The more the value of Cp, the more the material has the ability to store thermal energy. For example, the Cp of water is 4.18 kilojoule per kg degree centigrade, while that of the iron is 0.45 kilojoule per kg degree centigrade, and these values are at the room temperature. The value analysis shows that the water has around 10 times more heat storage capacity or thermal energy storage capacity as compared to the iron per unit mass. So this is the concept of the Cp, which we have studied in our previous lectures or in thermodynamics and previous concepts. K is an opposite of it. Cp is the material's ability to store energy. K, or thermal conductivity, is the material's ability to conduct the heat or conduct the thermal energy. For example, for water, the value is 0.607 watt per meter per Kelvin, while the value of K, or thermal conductivity, for iron at room temperature is 80.2 watt per meter per Kelvin. That shows that the iron can conduct heat 100 times more than that of the water in the same phase or in the same phenomena. Now you can see for Cp case, water was much better, but for thermal conductivity case, iron is much better. That shows that water is a poor conductor of electricity. So this is the concept of the K, which is correlated with Cp in a sense that for Cp, the higher the value, the higher the storage, while for K, the higher the value, the higher the ability of a material to conduct heat. So if we define the thermal conductivity, we can define it as the rate of heat transfer through a unit thickness of material per unit area per unit temperature difference. As you can see, we have represented by watt per meter per Kelvin. The high value of thermal conductivity means that the material which we are talking about is a good heat conductor, while the low value means that it is poor heat conductor or insulator. As we have seen that iron has higher value, so it is good heat conductor, while water has lower value, so it is comparatively poor heat conductor. Let's say that the thermal conductivity of pure copper at room temperature is 401 watt per meter per Kelvin. That shows that 1 meter thick copper, this is the thickness of the copper material, will conduct heat at a rate of 401 watt per square meter area per Kelvin temperature difference across the wall. So this is the overall definition and description of the thermal conductivity for a process which we need to understand, because thermal conductivity plays a vital role once we talk about the heat conduction phenomenon. Next part is that how we can measure the value of thermal conductivity. Now, if you look at this diagram, this is the sample material, and if I show it like that, this is the sample material boundary, And accordingly, this is first point. This is the second point or boundaries of this material. The insulation is installed across this material because we want to measure the thermal conductivity. Now the insulation is installed, and between the insulation and the material there is an electrical wire or electric heater that will supply the heat to this material. Now the insulation gives us the guarantee that there will be no heat leak or there will be no heat loss, and the amount of heat that will be transferred from the heater will directly go to the material. So we know the value of the thermal heat that will be transferred from the electric heater. Accordingly, we will measure the temperature gradient, that temperature at this point T1 and the temperature at this point T2. We will know this. We know the thickness of this material, which is represented as L. We know the area of this material, which is represented as A. So simply, we say the Fourier law as Q is equal to Ka dt over dx, or accordingly, if we rearrange it, it will be K is equal to L over A, T1 minus T2, which is dt into Q. We know the value of Q because we know how much heat we are transferring from the heater, and accordingly the insulation is installed to ensure that there is no heat loss or leak to the other media. Then we know the area, we know the temperatures, and we know the thickness, so accordingly we can measure the K of our material. Let's just read it, that a layer of material of known thickness and area can be heated from one side by an electrical resistance heater of known output. If the outer surfaces of a heater are well insulated, all the heat generated by the heater will be transferred to the material for which the conductivity to be measured. Then measuring the two surface temperature of the material when steady state has been achieved. When steady heat transfer is achieved, and substituting them into equation together will give the answer of the thermal conductivity. So this is the pattern of measuring the thermal conductivity of a material. After obviously the steady state conditions have been achieved and there is no change with respect to time. Coming to the final part of today's lecture, that what is the effect of temperature on the value of thermal conductivity. So with the increase in temperature for solids which are metals, the value of thermal conductivity decreases, and the typical behavior for this is the electron scattering. For non-metals, initially it increases, it gets peaks, then it decreases because of phonon scattering. For liquids, it decreases because of disrupted molecular paths, and for gases, it increases because of faster molecular motion. So these are the behaviors. We will study these behaviors in detail in our upcoming lectures. So I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer it. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.